Tests have been looking pretty good so far. I had graded.
You probably have a great one.
I've graded part ones. Everybody's part one, like with no curve. Class average is kind of like in that 78 to 80 range. So not too bad. We'll see. I'll have final, probably have overall grades put in by tomorrow morning, I would think. I mean, always.
Thank you.
So just to put a perspective of where we're at. So we're going to do 6.4 and 6.5 today. And we're going to have, we're going to do integration by parts, and then some diff-EQ stuff, and then we are done. That'll be enough stuff for test 3. That'll be the last test of the semester. Ideally, I'd like to do that before we leave for spring break. So we come back from spring break and it's just kind of like Mr. Kulik does a little bit of miscellaneous, this is good for you, fill in stuff, and then review that last month of April.
It's actually a lot of time.
Yeah, I think we did.
Stuff like boost our grade if we need it after test 3.
Yeah, perhaps.
Perhaps, sure.
I don't want to take an exam, guys, okay?
Thank you.
It's an AP course. You're not required to take an exam,
Isn't
period.
it if we don't have a 93, we have to do something, though?
No,
Or is that not a thing?
not for an AP course.
Well, still, I don't want to.
No, Talika, it's for regular classes. If you have a 93 and above, and 5 of you are absent.
Oh, so then why am I trying so hard? Oh, sorry, I can't.
Because it's good for you and you want to succeed in life. And you have high character. And you're not doing this for a grade, you're doing this to learn,
That's true.
right?
Yeah.
And if you think about it that way, it's a lot easier to try hard because you're just doing it for you now, right? All right. So that's kind of the overall plan at this point. The chapter 9 ideas are not terribly difficult. So this is something that I think we can probably do a couple of these sections together and get in and out of here and have plenty of time to kind of squeeze that test in before we leave for spring break so you don't have that dangling over us. I think that's probably best for everybody. But if it starts looking like you have a lot of stuff piling up that week of spring break, we can talk again. But try to plan for this one. I think this one would be one that I would not really want to move because, boy, after 10 days of tropical vacation, I don't know how much calculus you're going to remember.
It's actually pretty, it's like at the end of the month. So
Yeah.
I think it's pretty doable.
Yeah, I think I counted. I think there's like 9 class days or something after today.
Wow.
Which-
9 classes. 9, 8.
No. Well, 9 days this class meets. But yeah.
For the rest of the semester.
No, till spring break, I think.
Until spring break.
Yeah, it's till spring break, I think. And I think that I can finish the next set of stuff. Okay. So today we're going to do 6.4 and 6.5. We'll be done way early because it's not a lot to these sections. Neither one is terribly theoretical. There's not a lot of new concept here. It's very much kind of just some application ideas. So a lot of what we're already comfortable with, we're going to be doing again. So in section 6.4, we're talking about some application of using an integral. One of the natural applications is physics. So a little bit of physics for dummies here for those of us that haven't taken a physics course. Newton's second law boils down to force equals mass times acceleration. Now, if we think about this in calculus terms, we know acceleration is related to the position function. It's the second derivative of position. So we could also think about force as mass times the second derivative of position. And thank you. In a physics sense, work is equal to force times distance. Typically, force is measured in newtons and distance in meters. And work then comes out to be a Newton meter or a joule is the typical unit. I'm just trying to like little quick vocab, little quick formula. So for example, in a physics class, you might ask how much work is done in lifting a 1.2 kilogram book off the floor to put on a desk that is 0.7 meters high. And we're asked to use the fact that acceleration due to gravity is 9.8 meters per second squared. So I know force is mass times acceleration, right? And I know work is force times distance. And that comes out to be some stupid number, right? Uh, 8.2 joules. Very easy, right? Like this looks like a physics question, not a calculus question. Really is. And then part B says how much work is done lifting a 20-pound weight 6 feet off the ground. Physics students, what's the difference between weight and mass?
Weight mass is always the same.
Weight is a force, right? Mass is different than weight. So a pound is a weight. That's a force already. This is my F. And since that was the distance was in feet and the force was in pounds, our answer is going to be in foot-pounds instead of Newton meters, which is what a joule is. So what's similar between these two problems is that the force was always constant. If force is constant, it's a trivial, like Algebra 2 problem, we're just filling stuff into formulas. But what if a force isn't constant?
My guess is that's not.
So what we're talking about then is like an accumulation function. So the work is going to be the sum of all these little forces evaluated at some little tiny subinterval where we've taken a sample x from that subinterval times the little tiny length of that subinterval, right? And we're going to add those all up because the force is changing on each subinterval, right? And if we then take that subintervals to be infinitely small, what we have is an integral. So if our force is not constant, we're really going to just be using this integral function, where f of x is our force function and dx is our change in distance. Our infinitesimal, that's a hard word to pronounce, change in distance. Let's look at an example here. When a particle is located x feet from the origin, a force of x squared plus x pounds acts on it. How much work is done moving it from x equals 1 to x equals 3? So what is my force function going to be? Well, just x squared plus 2x, right? And then how is that particle moving? It's moving from 1 to 3. That's it. So we integrate, so we do the antiderivative and evaluate that from 1 to 3. When we do that, we get 50 thirds. Is everybody okay with me skipping the plugging stuff in, I hope, at that point, right? We did the hard calculus. Everybody's good? Okay. Another common application of forces is using springs, like boing, boing, boing springs. The principle that governs how springs behave is called Hooke's law. Hooke's law states that a spring stretched x units beyond its natural length is proportional to x, i.e. that the force is equal to k times x, where k is a constant specific to that specific spring. So like spring A and spring B will have different constants because they might be made out of different materials. They might be thinner, tighter together. All kinds of things could affect that constant, right? So let's look at an example here. It says a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to 15 centimeters. How much work is done in stretching that spring from 15 centimeters to 18 centimeters? So I know for the work question, oops, let's not write it that way. I know it's just going to be this, right? My job is I have to figure out K and then A and B. Everybody's okay with that? Since it's a spring, I know the force function is just Kx. Okay. So let's figure out K first. This information here is going to give me what I need for K. So I know 40 is the force that I need to hold some spring stretched from its natural length of 10 to 15. So what is the x in this case? 5. So I divide, and K is 8. Everybody feel okay there? Now, oops, that's not right. What'd I do wrong?
15 to 18?
What? Nope, 8 isn't right. What's wrong with the 8? Nope. It's a dumb problem, but it's important, dumb. Physics students, it is a units problem. Yeah, centimeters should be written as meters because a Newton is in terms of meters, so I have to turn that 5 centimeters into 5 or 0.05 meters. Woo! Yeah, right. That's like a oof. Really? There we go. Everybody's okay now? All right. Now, what should the bounds of my integral be? Well, same problem though.
Oh, 0.15, like 0.1, or 0.2, never mind.
The normal is 10, so it's just...
Right. So the natural length is 10, so we're only stretching it from
5 to 8.
going 5 to 8 past the natural length. And then converting those into meters. We got this, right? So when I do that, I get 1.56 joules. Again, I skipped all the calculus there because, like, my gosh, people, that's like the easiest integral you ever do. Plus, look at the number. You're for sure using your calculator for that anyways, right? Okay. So let's look at some more challenging. The last two problems will be a little bit more challenging. So the first one is a 200-foot cable is 100 feet long. I'm sorry, 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? So like we have some building, right? And there's my cable. Everybody's okay there? So we're having like some x value, and we're going to be slicing like a little delta x of that cable that we're moving. Is everybody okay with that notion? So when we're pulling this up, two things are changing, right? The length of the cable, right? It's getting shorter each time. And also the weight of the cable, so the force is changing each time, right? So if I know that we have a 200-pound cable that's 100 feet long, I know then 2 pounds per foot, right? So every 1 foot of cable I move, that's 2 pounds that I've moved. That's like my force. And what are we moving? Just an infinitesimal, like delta x, right? The distance I'm moving is going to be that x. So my work integral then is going to be the integral from something to something of, I'm just going to rearrange it as 2x dx. What are we going to be integrating from? What is the value of x changing from? Yeah, like 100 up to 0. Does that feel okay? And since we're in foot-pounds, again, like the easiest integral you're ever going to do, I'm going to skip writing the calculus steps for it because, like, my goodness gracious. Just the antiderivative of x squared, and we're plugging in 100 and 0. So just 100 squared. Nice. All right. This one sounds like fun. A tank has the shape of an inverted circular cone with a height of 10 meters and a base radius of 4 meters. It's filled with water to a height of 8 meters. Find the work required to empty the tank. Empty the tank by pumping all the water to the top of the tank. And it tells us as a hint the density of water is 1,000 kilograms per cubic meter. Okay, so I'm going to draw a picture here to kind of just represent what's going on. So here's my circular cone. There's my water. Everybody okay there? So I know currently when I first start pumping, that's going to be 2 meters, right? So this distance is going to be like my x, right? So I'm going to be, as the water goes down, the radius of this water is going to be changing, and the height of the water is changing both at the same time, right? This is just going to be some sample. So like there's the, some little tiny sliver of, like section of water there. That section of water, the height of that's going to be our delta x, right? That's the tiny little infinitesimal that we're going to be pumping out of there. But then this has a radius of r. Well, let's do rw. And the height, okay, everybody's okay with that? And then we have the height of the water that is remaining. I'll call that HW. Everybody feel okay? So first thing I'm going to want to do is I want to calculate a volume for the water when we're at some x. Everybody's okay with that? So I want my volume equation in terms of that x. So right now, so to do that, I'm going to write like a similar triangles argument. Actually, let's use black. So if I take like a triangle here from the cone, that's 4, and that's 10. So that's like my RW, and that's like my HW, right? Now look at that picture. Can I write HW in terms of x? Minus x, right? Does everybody see that? Yeah. So we can say then that like 4 over 10 equals RW over 10 minus x. So RW is 4 times 10 minus x over 10. And if you want, we can reduce that. Let's go ahead and do that, I guess, suppose. Does that feel okay so far? Okay. So, the volume of that little tiny slice that we're moving is a cylinder, right? That little slice I've made. So that's going to be pi r squared h. Now for that little tiny slice, the radius is going to be that 2/5 10 minus x. And the height of that little, slice is my delta x or dx. Now I know that mass is going to be density times volume. So I do that 1,000 times. I'm going to just do a little bit of cleanup here in a second. So I'm going to pull that 2/5 squared off of the big quantity, because I'm just going to put this stuff together and to make it one number, since it all reduced down and just makes it a little less busy going on there. So that's 160. So my force is mass times gravity. And when I simplify that down, I get 1568 pi times 10 minus x squared delta x. Okay with that? So my work is going to be the integral from, what height do we start pumping at? The first pump distance is 2, right? And the last pump distance is going to be 10, right? You're at the bottom of the tank. It's got to go 10 meters back up. Is everybody okay with that? So we'll go from 2 to 10. Oops. And then we have our force function. Times our distance dx. That's a tough one. Would be, honestly, on the AP exam, they're never this hard. And rarely do you even really get physics problems per se. More often than not, you get like just normal accumulation. Like here's some rate function, and the total is just the integral of the rate function. But that's the idea here. So if you do that in your calculator, you get like 3.4 times 10 to the 6th joules. Yes, Chanel.
May I come to the bathroom?
Certainly. Is that? So I have just, a handful of problems for us to work on from here. Most of them resemble that first example, where just like here's a force function, and it's going from here to here. How much work got done? Which is pretty much plug and chug. Use your calculator to make it faster if you want. If you want to practice doing the integrals, like not a bad idea, but if you feel solid there and you're like, I just need to get stuff done, I get it. Questions so far on this? Okay. 6.5 then is about the average value for a function. So we know how to take the average of a set of numbers, right? It's just the mean, right? You add them all up and divide by the length of the list. That's your average. But what if we have infinitely many values? Like different than the average value of a function. Yeah, I know. So let's think about something like the average temperature in a 24-hour period. How many temperatures are there in a 24-hour period? Infinitely many, right? Because at any instant you can take a temperature reading and write that down, right? But we talk about the average temperature for a day all the time. Must be a way to do this. So let's say that y equals f of x represents our temperature function on some interval from a to b. Like start a day, end a day. So to do this, what we do is we start by dividing that interval up into n equal length subintervals. We'll choose a representative sample from each of those subintervals, and then take the average of those values, right? Now note that because delta x is equal to the length of our subinterval is the overall length divided by n, that means that n is equal to b minus a over delta x. So let's make that substitution, do a little rearranging, and what we have is 1 over b minus a times the quantity of f of x sub 1 times delta x, blah, 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 all the way out to f of x sub n times delta x. That's a sum, a finite sum. That's a sum from 1 to n of f of xi delta x. And if we now take these subintervals to be infinitely small, that's the limit as n goes to infinity of this. And what are we talking about here? An integral. So the average value of a function is just 1 over b minus a times the integral from a to b of f of x dx. Really easy, right? It's just an integral. You just have an extra coefficient out front. Yes, Pierce. Yes, AVE is the notation that they're using here. So if we think about this, so the integral of our function is this area, right? Everybody agree? The average value, let's say we have this rectangle that has an equal area to the red shaded region. The height of that rectangle is just your F average. Because they both have the same width. So height times width is area. It's got to be the same area. So you can think about it conceptually as that. Yes. Oftentimes what we'll be interested in is after you calculate your F average, you'll be interested in, okay, what values of x on the interval from A to B does f of x have that average value, right? We'll look at some examples of doing that here in a second. But that's the idea. So let's say we want to find the average value of the function f of x on the interval from -1 to 2. That's it. So I get 2, 3, 1/3, and then 8/3. That's 6. 1/3 of 6 is just 2. So there's my average value. Everybody's cool? Go ahead. Not terribly difficult, right? Especially when presented in this way. Very straightforward. So if we think back to our temperature example from before, we might be asked, is there a time C such that the actual temperature is equal to the average temperature? That's that, right, that we're talking about. Now in this example, clearly, the picture I've drawn, clearly there is. Does there have to be? So if f is continuous, if our function is continuous on that closed interval from A to B, then there exists some number C on that interval AB such that f of C equals f average. Or that is, you can think about there's some height that makes this rectangle have equal area to that area under the curve, which I just showed you before, right, with the drawing. And everybody's like, oh yeah, sure, you could do that. Nobody had a problem with it. It seemed really obvious that that should be possible. And again, yes, this works, but the key is we got to have continuity, right? If we have discontinuity, all kinds of cuckoo crazy things can happen, right? Like, just think about something simple. Like if this is my function, so the area under the curve is like that, right? So like if I draw the rectangle, it's going to be something like this. And notice there's no value for the function that has that height, or has that value, right? Same as the height. So again, continuity, critically important there for that to exist. So I hate this, the way they've done this. right? We showed earlier that f_av is equal to 2. So really all I care about is solving that. So we can say f of -1 equals f of 1 is equal to 2. Everybody's cool? Seems easier. Let's do a kind of an abstract example here. And I like this because the vocabulary here is really important and the wording is really important because it confuses students all the time what we mean here. So let's read this here and maybe you'll see what I mean. It says, show that the average velocity of a car over some time interval from t1 to t2 is the same as the average of its velocities during that trip. So I'm going to just say, let's say we have two functions. S of t is the position function and v of t is the velocity function. Let's not write it that way. What's the average velocity? If I went 100 miles and it took me 2 hours, 50 would be my average velocity, right? So I have the change in position divided by the change in time. Everybody's okay with that? Make sense? The average of the velocities is going to be v average, which is an average value. Oops. Like that. What's the integral or the antiderivative of velocity?
It's place.
Position, yeah. And then if we just execute our definite integral, we see that they are indeed exactly the same. Everybody's cool? I wanted to do this example because, like, this verbiage is super common, especially on the AP exam. It's very easy to kind of get turned around about which one means which. So the average something is the slope. The average of the somethings is the average value function, or the average value. Does that, I know that's rough, but. And then I have a couple of examples, or a couple of questions for you guys to work on from the homework. That's it for these two sections. Relatively straightforward, I think. There's nothing like, I mean, this is kind of conceptual, but it's like really, I think, pretty easy conceptually. And the actual execution of it is really easy. It's just like, just an integral. It's an easy integral. You know, like, it's not a super big deal. Worst case scenario, maybe it's you have to do a u sub to do the integral, but like, not bad. And I don't even think really many of these have even a u sub to do. I mean, I'm looking 7 would. I guess 5 you would use a u sub to. So you get some u subs in there to do the integrals, but like not that big of a deal. Everybody's okay? What do you guys think? This is enough for today, I think, right? did 2 sections, even if it was quick and it was not too bad. I don't want to just like pile it on you. So for tomorrow, nope, I'm sorry, Thursday on the asynchronous day, I'm going to have my AP stuff for you to do. So just going to be some like, it's going to be like one of these little progress check or whatever, or review questions or whatever. I can't remember what they're called. That my AP makes them. The topics that they're going to be on are related rates and optimization.
Already told me.
Why, Mr. Kulik? Why?
I agree.
Because as we're getting closer to the end of the semester, we're going to be doing more and more review. I picked the 2 areas that I suspect that everybody feels the worst about from semester 1. And we're going to start with those because if that's the place where we feel like we need the most work, I'll grade it so you can see what it is. But I don't know, like if we're going to attach points to it. You know what I mean? Like I want to give you some kind of feedback that's meaningful, but I don't know that I need to attach points to it. In that kind of, you know what I mean?
Is it gonna be tons of questions?
Let's see. I picked the things already.
What?
How your what buddies?
Brookfield, we all went to the same
Me and
elementary
Toledo
school.
went to the same elementary school.
Oh,
So I've known Toledo
And
since I was
Ava.
5.
that's
Lucky
fun.
Chanel, because I'm since I was 5.
One day.
I cried on the snow. Rochester, so we met at nature camp.
Ooh, that sounds like fun.
Yes, we did.
No.
We saw me having my coffee.
I still remember that.
Mackinac? Yeah. Oh. We went to Mackinac and we went to space camp too. Yes, I remember that. Sorry.
You went to space camp?
Oh my god. Yeah, we went to Alabama for a week in 5th grade.
I wasn't in.
I was like crying. I miss my mom, but yeah.
But like, to be honest, it was
We got yelled at by the neighbor.
yes.
Did you go?
I didn't go to space camp. I was
So-
with my family.
Oh my god.
This is one question. That's it. So it's got 4 parts or whatever. That's one of them.
That's all we have to do.
And then the other one is this one. And this has just one question and again has 4 parts or whatever.
That's all we have.
That's it.
Okay, it's not even that bad.
Not even that bad.
Yeah, it was sorry.
You know what happened to Mr. Bob? I don't know. He was a king.
Wait, Chanel, do you remember this?
Did I fill up my water bottle?
Yes.
She passed away. I don't know. Do you know when she passed away?
2020.
Are you serious?
Right at the start of COVID.
Oh, that's so sad.
Dude, I was actually crying for like 4 days. I was so sad. Because like the day before, I was like looking through my own notebook or yearbook and I found like the like long like note sheet.
Cool. Can I go?